The next speaker is Tavish Pegram, who is a software engineer at Extent. He's a functional programming enthusiast, a Kotlin developer, Conway's Law aficionado, and Thai food enjoyer. Tavish is going to talk about how Unison can reduce an organization's dependency on programmer discipline and individual heroics. Go ahead, Tavish. Thank you for coming.
All right, thank you. And hi, everyone. I've been enjoying all the talks so far. I've been scrambling to update my talk based on everyone else's, so you might see some crude screenshots in here. So really quick, that was a good introduction, and so I probably don't even need this, but I'll just flash this on here. The only thing to really shout out is that I really like bad stock images of business people in presentations, so you'll be seeing a lot of that. So this talk is about Unison and its relationship with engineering discipline, all arising from, the one little big idea of Unison, and also just generally how cool I think Unison is. So what I would like to talk about is a few, I had to cut out all of the things I want to talk about because it's a 35-minute talk, but Unison features that I think are particularly interesting and how they relate to reducing the need for engineering discipline. And then also some very minor foibles or drawbacks from some of the big wins that Unison offers, but some ideas about maybe how those can be addressed and to become even bigger wins in this regard. So first of all, let's talk about discipline with regard to software engineering. And this will be a short detour before we get to the Unison bits, just to provide a background. So when I talk about discipline, I'm talking about doing what is correct, despite pressure, either internal or external, to do something that is less than. But lots of caveats for this. Software engineering is a game of trade-offs, so I don't want to make it sound like I'm saying everything has to be done perfectly all the time, or even that perfect is a real thing that's achievable or conceptual. Like that's not even like a real thing. But some examples of what discipline failing can look like could be choosing not to refactor the code because you're in a hurry, or you're just like not in the mood for it right now because there's tons of other stuff going on, or choosing not to write the rest of the unit tests because they probably won't be an issue. You've already covered the happy path, whatever, it's probably fine. Or taking on tech debt because you have a deadline coming up and you need to get that feature done ASAP. And, later I'm just going to tell myself that the world will change and there won't be deadlines after this one. And we can just come back and address all the stuff we've been punting on. So discipline is especially important because failure to stay on top of complexity in a software system leads to it compounding over time. So often the easiest time to address the problem is now, if not years in the past, and it'll only get harder to address later. For instance, a common thing you might see a lot is you're coupling something together a little bit to get it done now, such as the data model. Maybe you're using it directly, like the persistence layer model from some ORM, you're using it in the view or the presentation layer, despite there being like some service layer abstraction or domain model in the middle. And you're just like, I just got to get this working. This works fine. I'll refactor this later. But that coupling takes time and effort to undo, and I'm sure everyone's experienced that. And if you don't get to it right away, other maybe more junior people will start copying it. It'll be kind of come the default way it works, or people will start depending on that code, and then it gets harder and harder to actually go back and decouple it over time. I also want to clarify that I'm not accusing people who do these things as being bad or incompetent or anything like that. What I am trying to say is that complicated systems seem to have a natural entropy to them, and you must consciously identify the things that work against our discipline and find and design ways of working that make doing the disciplined work easier and more natural. So maybe the discipline, you're relying on discipline when you're pushing the boulder up a hill. There's an incline that's making it hard work. But if you could orient the boulder to go downhill, you're not doing that much work. It's kind of the natural way it's going. There'll be a lot of boulder metaphors in this. So really quickly, here are some of the things that in my mind, affect discipline. So first of all, process. You saw from previous examples, it's very hard to be disciplined with constant deadlines or project work or even prescriptive top-down work. There isn't time to invest in the platform. There's a deadline, and there's no deadline after that, and there's an infinite number of deadlines. If you're incredibly heroic and determined and iron-willed and you have a great reputation and the company wants to support you, maybe you can push back against some of these and fight for time to address tech debt or to refactor. But that's pushing a boulder up a hill again. The natural way of working in these processes is to be an undisciplined feature factory, which eventually leads to an unmaintainable architecture, like a big ball of mud, and work becomes harder to do. And people have experienced that, I'm sure. Team organization is a big one, mostly an application of Conway's law, or Conway's law states that design is constrained to the communication structure of your organization. It's hard to be disciplined when you want to design a solution, but it's hard to implement that architecture because it doesn't, your design is constrained by your organization structure. So you can't build the good architecture, you have to build some other architecture, or you have to fight against all of the ways that the organization is structured to build something. Now, individual knowledge and discipline, I feel like maybe is a bit self-evident, but if you don't know enough about a problem to avoid it or work around it, then you don't even know to be disciplined. And then also just people have different pain tolerances and willingness to fight for discipline. So even just individual discipline between people's varies. Tooling is a big one. I think Unison touches on all of these, but tooling is obviously one of the big parts we'll be talking about. And it's basically, if your tool encourages doing work in a bad way, then you have to not use the tool that makes work seem easy to avoid doing bad stuff. That's a big test of discipline. Versus if your tool encourages working in a good way, you don't need to think about it. You just use your tool. Things are nice, and you move on. Kind of like that. If all you have is a hammer, everything looks like a nail, sort of. And then the status quo is a big one. Usually, when you're working in an enterprise code base, you write code that looks like the code that's already there. When you want to figure out how to do something, you copy what someone else did to address the same problem. If you want to do something different or new, that's pushing a boulder uphill again. So to one level up, more broadly, instead of relying on discipline, we want to build pits of success, which we'll talk a little bit more about later, but you want to design your style of working to make it easier to do the right thing and harder to do the wrong thing. Very similar to that is we want to incentivize good behavior. So we want to design our working context to encourage and reward the behavior we want, instead of kind of the way most places seem to naturally work, where we kind of incentivize the bad thing, but then insist that individuals make up for the differences. So back to Unison. So this talk is about how Unison can be used now and in the future to build those pits of successes and to incentivize developers through a good developer experience to reward doing things that are considered good in engineering. To start with, refactoring, a big one. It's really, really hard to continuously refactor a code base. When you go to a tech conference, when you read books about engineering, about architecture, when you learn about Agile and other methods of working, a kind of an oversimplification of that is that they tend to talk about how you want to be reactive and iterative and to learn things and respond to things emergently. And that basically requires you to refactor all the time. If you want to do domain-driven design, it's kind of predicated around refactoring continuously with an emergent, ubiquitous language. But if you have deadlines and the refactoring gets harder the longer you don't do it and no one else is doing it, everyone's experienced that, I think. It's just more heroic, unsustainable work to just say, I'm gonna refactor this now, and I'm gonna ignore what everyone else is saying, or I'm gonna fight for time to refactor. But refactoring is a first-class concept in Unison, which is, I think, a theme that's going to be repeated a lot in this. The language itself provides tooling to make refactoring easier and more natural in day-to-day work. These screenshots are stolen directly from the Unison documentation about refactoring. in this screenshot, you can just trust me, there's a big arrow there. We've refactored it to go from 10 to 11 there, very minor refactor. But if you make a type preserving change, the Unison codebase manager will create the new definition for you. It'll update all the calling code to call that new definition. And from your perspective, everything just works. This is the same experience everyone else has when making a minor change. And then you can see it there. We've just added it. We've updated it. Everything is wonderful. But if you make a type breaking change, UCM will still create the new definition, but it will not update the calling code to call the new definition. Instead, it will determine exactly what code needs to be updated and then present them to you on demand with like the to-do command, or just right here, it happened when trying to update. So your code, and then because it's not updated, this hasn't broken anything. Like I've started a refactoring process. It's tracking exactly where I am in the process, and nothing's broken. Everything continues to work exactly like it did before. And this is really wild to me. This is like elevating refactoring to a first-class concept in the language. It's supported by the tooling. It's part of the language itself. And while continuous refactoring is a discipline, by elevating it to a first-class language concept, language level feature, it's been made so much easier and safer and more natural to refactor that the amount of discipline you need to just buckle down and refactor has been significantly reduced. Testing, everyone's favorite thing to talk about. Basically the same story as refactoring. And testing and refactoring are also very closely related. Well-tested code is easier to refactor, with a caveat about how you couple your tests to your code. But we have the same pressures working against us. The existing code could be hard to test, and then it doesn't have good tests, and it's hard to refactor to become testable. And then that's just, you got to come in and do a big rewrite, but you got this feature you need to get done. It's, the same story. But similar to refactoring, tests have been elevated to a first-class language feature as well. So this looks pretty cool, being able to just add tests as watch expressions as you work on your functions, and then just check them into the code base. It's very like REPL-driven workflow. It's very fun. It's very cool. It's got very quick feedback. As you develop a function, you're developing a test suite against it. But this isn't the only thing about this. One common issue with writing tests is that the code itself is hard to test because maybe it's very effectful, maybe it has a bunch of weird dependencies, or maybe the tests just take really long to run, so it's hard to get in a good test-driven development loop where you rerun all your tests every few seconds, because if your test suite takes 2 minutes to run, you're not going to run it every 10 seconds. That'd be wild. And I don't know about you, but for me, that means debugging and refactoring the test suite, and then maybe getting into it and then being like, this is going to take me days or hours. I'm going to give up. Well, Unison also has the advantage of being a pure functional language, which means it can make a lot of really cool assumptions about unit tests, like that they test pure code, and pure code is deterministic. So UCM is able to do a bunch of magic, and well, first of all, it caches your test results, and then it also can select which tests to rerun based on which of its dependencies have been changed in this group, which is just so cool. So you can just rerun the entire test suite every time you make any changes, and anything that isn't affected by your change is cached. Anything that is probably pure code that's easy to test and is going to run really quickly, and then it goes back to being cached. And you don't have to do any weird, I'm going to run this subset of tests, and then you forget about another one, and then you're caught by it later. It just makes TDD basically, like, why wouldn't you do TDD in this state? I want that feedback all the time. The need for discipline for doing that kind of work is significantly reduced, just because pure code tends to be easier to test. Testing is built into this. We've improved the performance with caching and knowing which tests to rerun magically. It's just a great experience. But there's more, because what if I make a breaking change and now I need to refactor my tests? So in this example, I've added an extra argument. but it knows exactly what I need to update. And you can also see something else I need to refactor from a different side project, just to plug test containers on Unison share. So take a look at that. But all of this is to say, by making tests a first-class concept and intelligently caching results by default, being a pure functional language, Unison gives you the easiest and best testing experience of any programming language, in my opinion. The barrier to consistently writing good tests and practicing something like TDD is reduced significantly. On to the next one, architecture. Architecture is a huge topic. There's a ton of books about it. There's a million talks about it. And it's great to read about it, learn from experience and experimentation and from other people. But it's so huge, and I'm sure a lot of people's experiences of working on code bases at scale is that you're spending a lot of time fighting to preserve a designed architecture, and it requires an enormous amount of discipline. You're spending time explaining and teaching the architecture to everyone around you, especially like newer, more junior engineers. You're writing a ton of documentation, which then gets stale. You're coming in and rejecting PRs that people have spent weeks working on and that they're very proud of, and you're like, sorry, this invalidates this architecture that we based on a book of 1,000 pages that you've never heard about. Or worse, you go on vacation and you come back and then you have to refactor out all of the changes from those PRs that you weren't able to project while you were on vacation. And that's not a good place to be in. It's sad for everyone. It's more boulder pushing, where it seems the natural state of the world is to destroy the architecture and then make you play the villain and tell people no all the time. So this topic specifically is covered in what I think is the original Pits of Success talk by Mark Seaman, which is on YouTube. Highly recommend it. That talk, I think, very convincingly argues that OO programming and maybe other styles can be really great, but it requires constant vigilance and discipline to maintain useful architecture, and it feels like balancing a boulder on a hill. Here's where I'm mixing boulder metaphors. But with a pure functional language, in his case Haskell, in our case Unison, or to a lesser degree just with kind of FP conventions that you could enforce with a compiler, hopefully, like suspend functions in Kotlin, you can get a pit of success where the boulder naturally stays where you want it. And it's a lot safer down there. You can go on vacation. This is in practice, and kind of a gross oversimplification of all those engineering books, is that trying to keep infrastructure and concrete definitions separate from pure business logic that's like kind of inherently what most of these architectures are going for as a gross oversimplification. It's also just kind of, I feel like, emergent from aggressive application of solid principles. And I personally like to just go with a ports and adapters architecture, just another name for similar concepts. But as Mark Seaman points out, Haskellers don't really know what ports and adapters is. Generally, I'm sure a lot of people do. But they tend to implement something like that anyway. And that's because Haskell is a pure language and it makes writing in pure code a little painful. Not so bad you can't do it, but enough that you want to minimize your use of it. You don't really want to spend all your time there. Unlike something like Python or Java, where you can just throw effects in willy-nilly and it feels like the most natural thing in the world until your architecture starts breaking down and your code feels untestable and you don't know if your code throws exceptions or what it depends on, etc. So you're forced to track impurities with the IO type in the type signature, and interacting with IO is not super fun. You have to do some mapping inside it. It's not the worst, but it's not great. It's extra overhead. So you naturally learn to separate out pure behavior from impure behavior so you can stay away from it. And from this example, it might not seem like a lot, but think about what your code base would look like if all the impure and pure functions were separated like this kind of naturally without you needing to teach people about it. You would have a ton more pure logic you could write tests for. You could naturally compose the impure with the pure at some point high up in your architecture, maybe some kind of service level. And at this point, you're just accidentally doing ports and adapters or the clean architecture or the onion architecture or whatever you want to call it, and no one had to know the name of it or read about it or anything like that. So Unison is the same, except even better. because you avoid all the monadic stuff, which I guess is an opinion, but I think abilities are a way cleaner way to kind of do this. And then the added benefit is that abilities also give you dependency injection, and they still enforce purity at the type level. They give you, you can track effects at a more granular level, and they also provide an abstraction tool for you to use. So, and even better, this is really the only tool for this in Unison. So you can't select a less good way to do this. Like if you're in an OO system, maybe you get really into inheritance, and that can get really hairy instead of sticking with composition. And then this ends up looking very, very similar to the Haskell example, because when you have an effect or when you have an ability, maybe it's not necessarily an effect, but if it eventually requires IO, it'll bubble up that way, and you don't always want to have a million different abilities in your type signatures, and it kind of naturally sorts itself out the same way. So this is the stereotypical example of fits of success for functional architectures from Mark Siemens' talk, except even better because abilities are great. So from there, I want to pivot into some of the really positive parts about Unison that have small drawbacks, in my opinion, with regard to discipline, and then maybe throw out some ideas about how those can be addressed in the future. So Unison, because code is structured data, it can be sent over the wire easily. So there were talks earlier today about how easy like distributed programming is, like communication with like over the internet, over the network. You don't need to have GraphQL or REST or whatever. You just send code because code's data. So nodes in Unison don't even need to have the dependencies installed ahead of time. Unison can figure out how to pass along function definitions, which is amazing. And then even more than that, if you browse some of the GitHub issues, there's talk about like just collapsing the boundary between front end and back end and just making it another ability, which sounds incredible to me for a lot of reasons. And I'm sure those are fairly self-evident, which is all incredibly good stuff. But there was something we used those difficult, hard boundaries for, and it was enforcing architectures and loose coupling and discipline. So one of the reasons we build microservices is that it enforces that the components are loosely coupled. I know there's like a technical independent scaling thing and separation technology, but the one I'm most interested in is you put a hard boundary around something, and now you're forcing, or at least trying to force a loose coupling, which is relatively effective unless you accidentally make a distributed monolith. And then you can also do cool stuff like align service boundaries to team communication boundaries, and then you're doing the inverse Conway maneuver. And you can have technical APIs reflect those same real life conversation pathways, cool stuff. And despite Unison having a big advantage of having a great type system and the architecture benefits of being a pure functional language, I'm still really worried that eliminating these strong boundaries will also eliminate the tool of enforcing this loose coupling, possibly naturally leading to one of the most elegant and well-typed big balls of mud architectures. So if anyone's ever worked in a big Python monolith where it's entirely disciplined, you can do whatever you want, you relies purely on discipline, it doesn't really work. So is there a way that we can preserve a sane dependency graph in Unison? And just as an aside, there are tools like this and other stuff. I'm familiar with Arch Unit, where you can write unit tests that enforce dependency graphs in like Java, or Java modules allows you to do a similar thing. So there's tooling that exists, but is there a better way to do this? So what if we followed what Unison has already been doing in talks today and from earlier in this talk, and just made this a first-class Unison concept, managing boundaries and dependency graphs as code in Unison? So I've seen discussions in the Unison Slack, which I'm failing to find now, which is why you just have this guy holding a light bulb, about making a namespace a first-class concept. And then maybe through UCM, we could just set in plain Unison code what namespaces are allowed to consume this namespace directly, which aren't, what functions and types we should expose as a public API, which should be kept private internal. Like let's let's like design the dependency graph for our namespaces. And then I just scrambled to put this in from Simon's talk immediately before this. But like, this is kind of like exactly what I was thinking. Like, can we just add a type so we can, as code, we can specify what we want. So maybe we could piggyback on a project. Maybe we need a similar thing for namespaces. I'm up for whatever makes sense. But since UCM is already playing the role of a GitHub version control system, maybe we should also introduce other concepts as code, like contributors or like user roles and code owners and admins, and set who can update these things. Because then we get back our hard boundaries. We can design the boundaries of the system in code. We could say this collection of namespaces or this project or this collection of projects is a service, and these are the APIs they expose as Unison code. And we've enforced those boundaries rigidly, like you can't reach into it. Maybe we could even say you're not allowed to look at it, though that seems a little extreme to me. But then we get this weird, almost paradoxical benefit as well, where because it's code, it's also easy to change the boundaries. Like you probably still want permissioning for this so that people don't just arbitrarily change the boundary. But if you spin up a microservice to have a hard boundary, and then you're like, ooh, I should change this boundary, that's a big change. You got to spin up a new service. You got to do a ton of refactoring. It would be so cool if you could just, maybe your team lead has admin access to this, and they can just be like, all right, let's redesign it as a team. Let's move this namespace into the service, and we can go through a structured refactoring session. And great, we've redesigned our system boundaries. They're still very hard boundaries, but at the same time, it's very flexible. It's like having your cake and eating it too. So you got Unison code shooting around the network, breaking down the boundaries between front end and back end, but you still have this thoughtful, designed, and enforced boundaries around services, which is very exciting for me. Next one I want to talk about is just kind of the dev experience with really type safe and functionally pure languages, and how they either do slow down or feel like they're slowing down development on a new project that you might be bootstrapping. So there's a reason that these kinds of frameworks are popular despite a lack of type safety, and often what sounds like a lot of difficulty in scaling. They seem to hit a point and then everyone's like, we got to get off of this. And I think there's like something really good about doing convention-based development. And one, it gives you big assumptions that framework developers can take advantage of to just generate a lot of boilerplate code for you in ways that are almost magical. And there's other options here. You can use it's probably out of date now, but like Yeoman, you could work to build generators yourself. I know you can take some from the community, but I've personally found that this doesn't quite fill the hole that I'm thinking of here, and it's still just generating text files. And then there's Yesod for Haskell, which is pretty good. But I still feel like you also get this other thing where you're at the whims of someone else's conventions, which maybe aren't a great fit for you. And even I don't have an enormous amount of experience with Yesod, but even then I feel like Unison can do better. And so just from personal experience, and I assume other people have this experience as well, it can feel really slow building out a scalable architecture from scratch. Like if you were just like in Python, I want to do a really intense ports and adapters architecture. Maybe it's premature for that, but it just is slow. It feels slow. People are like, just get it working and then refactor later. But like, why? You want it eventually. Or even just with like the benefits of a type safe language is that you're forced to handle all the failure cases, but it feels slow when you're just like, I need to get a prototype done. I need to get something out the door so we can iterate on it. And it's because of the feeling of going fast often means cutting corners or prioritizing getting something that barely works out the door instead of the discipline thing, which can completely be a fair trade-off, depending on where you are in your company or your work's life cycle. And I expect Unison will have similar problems getting adoption for early projects or rapid prototyping because it's all of the positive aspects of it can make it feel slow. Though, again, I still think these are great things to have because these tools make maintenance and scalability a breeze and a dream. So it'd be nice if we can bridge that gap somehow. So again, we have UCM and code as structured data. Can't we make something really amazing to solve this? So in Slack again, and there's other conversations in Slack if people want to look around for it, but we've been talking about introducing a code-based ability. And I say we as if I am playing a big role in this. It's really everyone else, and then I'm just taking screenshots. But that would a code-based ability that would allow for code generation, and again, just make that also just plain Unison code. So this was, I think, in the context, maybe this one wasn't, but when I was introduced to this concept, it was within the context of talking about generating types from a GraphQL schema or a protobuf schema. But I think there could be much more interesting applications of this. Because if well-typed code generation is a first-class language supported feature in Unison, where you're not dealing with like arbitrarily generating text that's put into files, and like testing that's hard, and working with that's hard, and you lose a lot of types safety that makes the language so nice to work with. But if we made it an ability and we made it all Unison, and the API was sufficiently easy to use and well designed, maybe teams can build code conventions into UCM code generation tools. Like if that was sufficiently easy, that would be so cool if that was just a part, like, oh, like even the Unison documentation mentions a recommended structure for your projects. Like what if there was just code generators that would bootstrap that stuff for you, and then the community could maintain them? Which, what if it was this easy to, if it was this easy to make code generation tools, and what if this was something you could just type into UCM, and based on some kind of community maintained scaffolding tool, or one that your team maintains themselves, we're just able to spin up all the boilerplate for you. And then because it's all Unison code, you get all the other benefits. Like the scaffolding code is easy to refactor because it's Unison code, so you can go through structured refactoring. You could generate full stack or distributed programs, so you've co-located infrastructure, because infrastructure is also just abilities, and because it's all Unison code, so you could code generate like distributed programming and deployment infrastructure, like just crazy stuff to me. That sounds so cool. And you could, documentation is Unison code, tests are Unison code. You get the benefits of all of that as well when you can generate this. And because it's just an ability, it should be easy to build and maintain and share. So I'm imagining a future where the community maintains several different, I think different is important, so you have the options, but several different opinionated scaffolding libraries to bootstrap like a prototype or a new service for a brand new company that wants to hit the ground running, but also build in scalability. But also hopefully make it sufficiently easy that individuals and teams could easily make their own to codify the conventions that they agree upon internally, and reduce the need for discipline to maintain them, because generators seem like a great way to maintain discipline. Instead of saying build this here and there and here's the reasons to do it, you just run your generator. It puts the code where the team agrees the code should be put, and then you fill in the rest. Well, that was a lot of stuff. I think I was talking pretty fast. But in conclusion, emergent from Unison's big idea of content addressable code, we get the ability to raise disciplines like refactoring and testing to language level features, making them easier than ever to do. The choice to make Unison a pure functional language means that clean architectures emerge naturally without needing to yell at anyone or read a million books, though I do think people should still read the books, but you're not hand slapping. UCM does that for you. It also further improves the testing experience, making TDD a no-brainer. In fact, I think UCM should probably just default to running all of the tests every time you save anyway, and just force people to think about the tests as they're working. And even the small trade-offs to the other Unison big wins, like its distributed programming story or the type safety, can be turned into even bigger wins by continuing to build on the existing language features to reduce discipline further with boundaries as code and code generation by convention. Cool. And that's all I got.
Awesome. Thanks so much, Tavish. That was great, and I'd love to see how people are talking about Unison in ways other than just writing code to accomplish this task. Like looking at how it's solving these social problems is really interesting, and I want to talk more about that. So we're going to jump over into the Q&A room, and we will pick up questions there.